Hello, this is Mr. White, and this video is on recognizing the f of g of x, g prime of x pattern, and I also call this process unchaining, or the unchain rule. Here are the three exercises. Let's get down to business. Now, before we do this indefinite integral problem, or this anti-deriving problem, let's first just remind ourselves exactly how the chain rule works for deriving. Let's say we had a similar function here that we were going to derive. So let's say we had x cubed minus 2 to the 7th power, and we want to not anti-derive, but derive that. Well, we know that applying the power rule, we'd get the 7 x cubed minus 2 to the 6th power. And it's the chain rule that says I have to multiply that by the derivative of that inside function, x cubed minus 2. So I have to multiply by 3x squared according to the chain rule. Well, I'll go ahead and point out that is exactly the pattern that we're going to be looking for, where the g of x was the x cubed minus 2, the f of x was the 7 blank to the 6th power, and then, of course, the derivative of the inside function is g prime, or 3x squared in this case. And let's consider now when we integrate both sides of this equation. So we do integral dx. Integral dx. Let's go ahead and do it down here too. Integral dx. Well, on the left-hand side, integration and differentiation are inverses of each other, so they essentially cancel each other out. And in fact, let me go ahead and just erase those. Again, the differentiation and integration completely cancel each other out, and there is only one little thing that we'll have to do to make this completely correct, and that is, of course, add that pesky plus c. So notice what we have here is the inner function, g of x. That was our inner function there. So that was the g of x, and it's plugged into the antiderivative of the outer function. So over here on the right, we had 7 blank to the 6th power, and when you antiderive that, you get blank to the 7th power, right? So that's the antiderivative of the outer function. In other words, the antiderivative of little f, which we call big F. And we still do the plus c here. So reminding ourselves of how the chain rule works for differentiation, recalling how this chain seems to kind of appear out of nowhere. When you derive, we need to understand that it will disappear back into nowhere when you go in this direction, when you anti-derive. Notice that that 3x squared just disappeared when we went over to this side of the equation. That seems to be the main sticking point in my experience with students, is they constantly ask, what happened to the 3x squared, or whatever the equivalent expression is? And we need to completely understand why that needs to go away. So let's just keep this down here, and let's tackle that problem up above now. I'm going to move it over a little bit and line it up with this function down here. And let's try to set up a similar structure here. So I'm recognizing that x cubed plus 5 is the inner function. And when I ask myself what's the derivative of that inner function, we get 3x squared. And the x squared that we have just hanging out on the outside there is very similar to the 3x squared. It's off only by a multiple of a constant. So what I can do is put the 3x squared there. I could put the 3 there because I want a 3x squared, but in order to make that okay, I need to put a 1/3 on the outside. 3 times 1/3 equals 1. It's okay to just insert that into the equation, or into the expression. And now I've got my g prime of x, that 3x squared that we had down here, right? So let's go ahead and rewrite that as integral of x cubed plus 5 to the 4th power times 3x squared with the 1/3 on the outside and our dx at the end. And remember how it was the outer function It was the 7 blank to the 6th power down here that got anti-derived to give us blank to the 7th power over here. We just need to do the same thing up top. So if I really just focus on the outer function, that blank to the 4th power there, when I anti-derive that, I'm going to get blank to the 5th power with a 1/5 in front to balance out the 5. And I trust you fully understand now why that 3x squared went away, just like it did down here. However, do notice that this 1/3 here, that was not present in this problem down here. That 1/3 does need to come along for the ride. It was outside the integral, so we'll keep it along for the ride. Let's not forget the plus c. And let's go ahead and go back and recognize the inside function, the x cubed plus 5, and put that in here. So this is the point where you pause the video, take a breather if you need to. Make sure you've completely got all that. I'm going to go ahead and clear this away. And let's finish off this exercise. Let's bring this down here and then simplify it. So our final answer will be 1/15 x cubed plus 5 to the 5th power plus c. We'll put a box around it. And let's proceed to check the result by differentiation as we were asked to do. And I do insist that really is a great practice to get into. So let's check by doing d over dx of our answer. So applying the power rule and the constant multiple rule, 5 times 1/15 will give us the 5/15 times x cubed plus 5 now to the 4th power, where we recall the chain rule, 3x squared. The derivative of c here gives us 0, so we don't worry about it. I see that this 3 and this 5 give me 15 over 15, so that all divides out to just 1. And what I have left over is x cubed plus 5 to the 4th times x squared. And if I go back to our very original problem, we see that that is exactly the integrand that we were trying to anti-derive in the first place. So check. All right, let's go on to the next exercise. Here we are asked to solve the differential equation, and that means solve for y. And as far as how we get that y by itself, I'll remind you, we've seen this before, but it's worth going over again, that if I multiply dx on both sides of the equations, dx divides out on the left-hand side, I end up with dy equals 10x squared. And while we're at it, let's go ahead and rewrite this in a more calculus-friendly way. Let's write 1 plus x cubed, and the square root means it's raised to the 1/2 power, and the fact that it's in a denominator means that it's negative 1/2 power. And we've got that dx here. And integrating both sides of the equation, let's put a little implied 1 there. Integrating 1 with respect to y gives us y equals this integral here. And so again, if we were tasked with solving for y, and y equals this integral, we see that this request to solve the differential equation is exactly the same request as being asked to find this indefinite integral. Now this looks a lot like the previous exercise, and we'll proceed to solve it in a similar manner, and I'll go a little bit more quickly this time. So if I bring up the f of g of x, g prime of x pattern, we once again recognize that on the inside we've got our g of x function, and if we ask ourselves what's the derivative of that, it's going to be 3x squared, which is off by a factor of some constant from 10x squared. So let's do this. Let's write the integral, and that 10 isn't really doing us any good. We want 3x squared, not 10x squared. So let's bring that 10 to the outside. And again, you can always do that with constants. I emphasize only constants may be brought in or out of an integral. And let's write the rest of the integral expression. x squared 1 plus x cubed to the negative 1/2 dx. Now let's do the same thing we did last time. Let's put the derivative that we want. Again, we want a 3x squared, which is the derivative of this. We want a 3x squared hanging out here, so let's put the 3x squared. And remember, we justified putting the 3 in there if we balanced it out by putting a 1/3 outside the integral. And this is the point where I recognize that that chain there, that 3x squared, is going to go away when I antiderive. And as far as what I'm antideriving, I'm wanting to antiderive this outer function. So in the last exercise, I even covered up the inner function just so we could really focus on antideriving that blank to the negative 1/2 power. So antideriving that blank to the negative 1/2 power will give me blank to the positive 1/2 power. I just added 1 to this exponent, right? And that 1/2 exponent up here needs a 2 right here to balance it out. Now in the antideriving process, again, the 3x squared goes away, but this 10 and this 1/3 on the outside come along for the ride. And of course, since we've just antiderived, we'll do the plus c. And we'll go ahead and acknowledge now that inner function, 1 plus x cubed. So let's combine this 2 times 10 times 1/3. That's going to give us 20/3 times 1 plus x cubed to the 1/2 power. You could write that as square root of 1 plus x cubed, but I generally just prefer the rational exponents or fractional exponents over radicals. And that is our answer. Now, we were not explicitly told this time to check by differentiating, but again, I'm insisting that that's always a good practice. So let's do that real quickly anyway. And again, I hope you'll adopt that as a practice as well. So let's derive this function. 1/2 times 20/3, that's going to give us 10/3 times 1 plus x cubed. Now that 1/2 gets reduced by 1, so it falls to negative 1/2 times the derivative of the inside, 3x squared. The derivative of the constant is 0. This 3 on the bottom and this 3 on the top divide each other out, cancel each other out, and I've got 10x squared. And this 1 plus x cubed to the negative 1/2 power, that's the same as 1 plus x cubed to the 1/2 power in the denominator, or if you prefer, square root of 1 plus x cubed. And we see that that does exactly match the original problem that we started with. So, check. We've got our correct answer in the box there. All right, let's go on to our last exercise. This exercise, in addition to presenting the typical challenges that trig problems tend to present, is a case where it's not immediately obvious which piece of the puzzle represents the f of g of x and which piece represents the g prime of x. Let me show you what I mean. If I rewrite this integral as tangent x to the 1/3 power times cosine x, and since that cosine's in the denominator and being squared, it's raised to the negative 2 power dx. And I notice that there's two composite functions here. Tangent of x could be our g of x plugged into an outer function, blank to the 1/3. Or cosine x could be our g of x plugged into an outer function of blank to the negative 2 power. So again, it's not immediately obvious what our g of x is, but let's reason it out this way. Let's consider that if g of x is the cosine x, then that means that g prime of x would be negative sine x. And so I need to have a negative sine x hanging out over here, but no matter which trig identities I apply, there's no way I'm going to turn tangent of x to the 1/3 power. There's no way I can manipulate that and turn it into a negative sine x. So that doesn't look very, very hopeful. So let's now consider the other possibility. Let's say tangent x is our g of x, and then g prime would have to be secant squared. So is there a way that I can turn this thing hanging outside the function? Is there a way I can turn that into secant squared? Well, absolutely there is. We recall our trig identity, our basic trig identity that says that secant x is just cosine x raised to the -1 power. It's the reciprocal of cosine x. And therefore, if I take secant squared of x, that's going to be cosine x to the -2 power. That's exactly what we've got hanging out here. Perfect. So let's rewrite our integral as tan x plugged into a blank to the 1/3 outer function times the derivative of tan x secant squared x dx. And now this fits the pattern g of x, g prime of x, tangent x, secant squared of x. The f is the blank to the 1/3 power. So notice that in order to sort all that out, we needed to be solid in our basic trig identities. For example, secant x equals 1 over cosine x. And we needed to be solid in our trig derivatives, knowing that the derivative of tan x is secant squared x. So recalling from the previous exercises how this chain goes away, and it's this outer function f that we really end up anti-deriving, let's go ahead and do that. We'll cover up that inner function, just allowing us to focus on the outer function. And when I anti-derive blank to the 1/3 power, I'm going to get blank to the 4/3. 1/3 plus 3/3, right? And I need a 3/4 out here to balance it out, plus c. One more time, that secant squared just went away due to the unchaining effect. And now I recognize the inside function, tangent x, and that is our final answer. If you preferred, you could write tangent to the 4/3 power x. You can use that shorthand if you prefer, but I don't really care. So let's check at this time. Let's take the derivative of our final answer. And 3/4 times the 4/3 will give us just 1 times tangent of x. Subtract 1 from that exponent of 4/3 and we get 1/3. Chain rule says multiply times the derivative of tangent x. Secant squared x, derivative of c is 0. We compare that to the original integral, and tangent x to the 1/3, cube root tangent x, check. Secant squared x, again, that's the same as a cosine squared x on the bottom, so check. So we have our final answer.